Okay, welcome back. Next video, what we're going to do is we're going to extend the idea of increasing and decreasing functions and add an additional interpretation step. An extrema is a fancy word that means maximum or minimum value. The way that we will find maximum and minimum values of functions is we're going to look at pictures like this one, like in the previous example where we had regions of increasing separated by regions of decreasing, and examine where a function switches from increasing to decreasing or from decreasing to increasing, and carefully interpreting that to indicate whether a function has a maximum or minimum at that location. You'll see what I mean. So right now we're limiting ourselves to locations or x values where the derivative is equal to 0, but we'll quickly extend this also to x values that make the derivative not exist, because those can be locations of max and min as well. So the big picture is that a signature of maximum or minimum is that the sign of the first derivative will change from one side of that x coordinate to the other side of that x coordinate. If it's a maximum, so if it looks like the top of a hill, notice that to the left of that top of the hill it's increasing and to the right it's decreasing. So the derivative went from being positive to instead being negative. And we can have weird shapes like this too. This is called a cusp. The derivative is not equal to 0 at the top. The derivative does not exist at the top, but we would signal the presence of a max by looking at the increasing versus decreasing behavior of the function. On the left-hand side, that graph is increasing, so it has a positive derivative. On the right-hand side, the graph is decreasing, so it has a negative derivative. And we have similar pictures for minima. So we also, at the bottom there, it says we need to check places where f prime of x is discontinuous, and that's to capture the cusp type of a picture. So I'll draw that again down here. So that's to find features like a cusp max or a cusp min. And the other one the other one's just for smooth max and min. So to further, I guess, quantify or qualify what is a max and what is a min, here's a graph that has a lot of those things, a lot of max and a lot of min. One definition of a max is it is the location where a function looks like it's the top of a hill. And a minimum would be a location where the function looks like it's at the bottom of a valley. So in red, all the maxima, or the tops of hills, are labeled. And in purple, all the minima, or bottoms of the valleys, are labeled. Notice that it is possible, now this graph doesn't have it, so I'll draw another one. It's possible for a local minimum, or relative minimum, to be higher than a relative maximum. So I'll show you that with a quick picture. So there's a max. Okay, so there's a graph where there's a min, a local min, or relative min. They mean the same thing. So relative, also local. Local min is higher than this local max. a local min can have a higher y value than a local max. And a local max can have a lower y value than a local min. So I could draw an analogous picture of that. It would look like the one on the left-hand side, but it just flipped up and down, flipped, reversed in the vertical direction. So that's why the word local or relative is important. It just indicates that it looks like the top of a hill locally or nearby. So if you were to be sitting, let's say, if you lived in this city, where that was the city at the top of that hill there, you would think that the low point in your city was that local min. You wouldn't think, oh well, I mean, you wouldn't think of it as that point, even though it's true. You wouldn't think that that point is lower than the peak of a hill that's far away somewhere else. So that's the local aspect of it. Does it behave like a bottom of a valley locally? Does it behave like the top of a hill locally? And relative is just another word for local. That's a qualitative description of the picture. A more mathematical description is as follows, and it's equivalent. I don't like reading paragraphs of math, but I'll read this one. A relative maximum can be defined as follows. A function f of x has a relative maximum at x equals k if there exists an open interval between a and b that contains k such that f of x is less than or equal to f of k for all x between a and b. So it's not a very friendly definition. I'm going to draw a picture of the definition and show you that it's the same definition of a max that we saw with the graph. So I'm going to say that there's a maximum at x equals k. It has a y value of f of k. Now here's my open interval between a and b. F of a, f of b. So the graph will look something like this. So f of x has a relative max at x equals k if there exists an open interval between a and b that contains k such that f of x is less than or equal to f of k for all x between a and b. So you can't, if you're looking at nearby x coordinates and plugging those into the function, this number that you're getting is smaller than the y value that you get at x equals k. You're not going above it. You're less than or equal to it. That's how that paragraph definition matches up with this definition. It's just a way to mathematically describe or algebraically describe what the top of a hill looks like. That if you take a little step to the right or a little step to the left, if you're on top of a hill, then taking a step away from that peak is going to bring you lower, not higher. That's all. Likewise, for a minimum, you're at a minimum if you look around the x coordinates in the vicinity of that minimum, all the y values are lower, all the y values are higher. So f of x at other x values that are around that x value are giving a higher y value. They're giving a higher output. So they're larger than or equal to f of k. So if you're sitting at the bottom of a valley and you take a little step to the left or a little step to the right, your height or your elevation is going to go up. That's an equivalent and perfectly well-defined mathematical algebraic description that matches with that picture. That's what a minimum looks like. Taking a little step to the left or to the right, away from the minimum, raises your elevation. Now, it has to be local, it has to be a small step. If you take too big of a step, so let's say you start here, you take a gigantic step, your height goes down. So you say, oh, well, I'm not at a minimum. So the local part is important. It has to be a small step. In fact, it can be infinitely small. Now, up to this point, you may be under the impression that every time we find a critical point, or critical number, every time we find an x value where the derivative is equal to 0 or where the derivative does not exist, that's going to signal the location of a local max or local min. Unfortunately, that's not the case. It can signal other things as well. It can signal what's called an inflection point. So the max and min are indicated in blue, another max is indicated in purple. Inflection is indicated in green there. And what an inflection point is a place that something interesting is happening with the second derivative. And we'll talk about that later. But it's not a location of a max or a min. Another thing that can happen at a critical number or critical point is that the function can have what's called a vertical tangent, where the slope of the tangent line becomes infinity or minus infinity. The ones on top, the three types of things that can happen on top, they happen where the derivative is equal to 0. So you set the derivative equal to 0, solve for x. All your solutions will give you one of those three things. It has to give you a max, a min, or an inflection point, or just a plateau, just straight across, nothing interesting at all, like no feature. So for example, if the function is just a constant, derivative is equal to 0, does not mean there's a maximum and an inflection point, it's just the function is just a horizontal line. So I just excluded that case from the slide. The bottom two, those pictures come from the derivative not existing. So if you take the derivative and you end up with a denominator that can potentially be 0, this is the main way that this happens. It can happen in other ways as well. But if the denominator can be equal to 0, so you end up dividing by 0 for the derivative, but that x value can be plugged into the function, so it's in the domain of the function, then the feature will look like either a sharp corner or it'll look like a vertical tangent. And we'll have to use the increasing and decreasing test to determine which it is. So these are all different types of graphical features. We could stitch them together and make some type of Frankenstein graph that has max and min and corner min and inflection points and vertical tangents. So graphs can have multiple features at the same time. What that leads us to, those pictures and the requirement that we need to not just set the derivative equal to 0 and solve for x, but we also need to diagnose whether those points are max, min, or something else. It leads us to what is called the first derivative test. The first derivative test works as follows. We find the critical points. We've done that already. We do that by taking the derivative, setting it equal to 0, and finding where the derivative does not exist. Now we have to add a step here. We have to make sure that these x values are in the domain of the original function. That's not going to cause a problem for x coordinates coming from the derivative being equal to 0. It's going to cause a problem potentially for x coordinates coming from the derivative not existing. So that's really important for looking for local max and local min. It has to be in the domain of a function to have a max or a min there. You have to be able to get a y value. If you can't plug the x value back to the original function, you can't get a y value out, so it can't be a max or a min. Anyway, so we make a collection of all the x values that fit this criteria, that the derivative is 0 or the derivative doesn't exist and the x value is in the domain. We make a big list. Then we make a number line. We create test values. We plug those test values into the first derivative and we check if the first derivative is positive or negative at each of those points, and that tells us if the function is increasing or decreasing. If the derivative changes from positive to negative, so changes from increasing to decreasing, that means that there's going to be a local max at that location. And if the derivative changes from negative to positive, so it switches from decreasing to increasing, that means that there's going to be a local minimum at that location. and if the derivative does not change sign. So if it's positive on both sides of the critical number, or negative on both sides of the critical number, then it means that there's no local max or no local min there. There's something else, probably an inflection point. So I'll show you this in action. Hold on. So why does that last part, the interpretation of the derivative, why does that make sense? So if we have a derivative that's switching from positive to negative, so switching from increasing to decreasing, this is what it looks like. It's going up, then it's going back down. And in between, there's a derivative of 0, or the derivative doesn't exist. Either way, it looks like this. It looks like a maximum, going up and then back down. Likewise, if the derivative is switching from a negative derivative to a positive derivative as we cross a critical point, then that's what a minimum looks like, something that goes down and then back up. So at least this definition is intuitive. It matches up with the graphical definition of a local max and a local min. We'll do one nice, very, very nice example. Find the relative max and relative min of the function f of x is x to the power 4. So we'll start by taking the derivative. We get 4x to the power of 3. We set the derivative to 0. We get one solution. X is 0. So that's our critical number. We're going to get the y value out. We might as well. Y equals f of 0, which is 0 to the power of 4, which is 0. So our critical point is 0, 0. I said we might as well do this because it's a good habit to get into, plugging your critical numbers into the original function. This checks the domain, and later on you're going to need the y value anyway to get the entire point, get the entire max and entire min. Okay, now we make a number line. This is a polynomial, so our number line extends over the entire number line, or the entire real numbers, from minus infinity to infinity. We're cutting it at 0, since that's our critical number. Now I'm going to choose two test values. Oh, I'm going to pick -2, and I'm going to pick +3. Oh no, I changed my mind. I'm going to pick +1. What made me change my mind is I looked at the derivative and I realized I have to plug it in, and I don't really want to plug a big number into there. Okay, now I'm going to plug in the test values. F prime at -2 is 4 times -2 to the power of 3, which is 4 times -8, which you can go ahead and multiply if you want, but I'm too lazy. I don't feel like multiplying that. I'm just going to say it's negative, and then indicate that the function is decreasing. Decreasing on the interval from -infinity to 0. Now the next test value, I'm going to plug that into the first derivative, f prime of 1. That's 4 times 1 to the power of 3, which is 4 times 1, which I'm not even going to multiply that. That's how lazy I am. I don't care to multiply 4 times 1. I just care, is it positive or is it negative? And it's positive. That means increasing. So f of x is increasing on the interval from 0 to infinity. So up arrow. We have it switching from decreasing to increasing. Thus, f of x has a local min at 0, 0. That's it. And again, relative means local. They're just synonyms. They're the same. They have the same meaning. And we'll continue in the next video.